Hello, we're going to show you how to deal with a mess that's on an inclined plane today. So here we have a box on a ramp or an inclined plane. That inclined plane is frictionless. And I have a simple question. I want to know the magnitude of the acceleration of the box when it's let go. Okay, so we could try to do this the way we've always done them. So I'm going to start doing that, but we're going to find out that that is actually not a good way to do this. So if I draw a free body diagram of the box, here's the box. Well, I've got the force of gravity, which in this case would be 98 newtons. I've got the normal force with the incline. Since the incline is tilted, the normal force will also be tilted. Remember, I need the normal force to be perpendicular to the surface. You know what? That's going to be really annoying. I'm just going to write Fn for normal force because I don't want to write the whole word normal every time. Okay, so here's my free body diagram. I do need some axes so I can show this 30-degree angle. So I'm going to make a little axis here, some axis. If you do some geometry, you will find that if the inclined plane has an incline of 30 degrees, then that 30 degrees is going to end up on my free body diagram right here. That's where it ends up. Okay. Now, here's the thing. Here's my free body diagram. Usually from here, we would write, Newton's second law in the x direction and in the y direction. Okay, but the problem is, in most of our problems before, like either ax or ay was 0 and the other one was just a. It was just acceleration. But unfortunately for this one, when this box is going to go, if it's going to accelerate, it's going to accelerate this way. I think you can all see that acceleration would be down the ramp in this case. So the problem is that for ax and ay, they are not the same. They are also, it's not binary in that one has a value and one is 0, because I am essentially treating this as a vector, and I would have to go and find, here's ay, and here's ax. And I'm not saying we couldn't do that, because we know angles. I know that 30 degrees would be here. I'm not saying it couldn't be done, but why do things the difficult way? Why? There's no reason to. This is too hard. Okay? It can be done. It's just too hard. So we're not going to do it this way. Okay? Instead, we're going to make a small change to our free body diagram that's going to make everything just a little bit easier. And that is, instead of using the traditional x-axis is horizontal and y-axis is vertical, we're just going to turn this thing so that the x-axis is along the plane and the y-axis is perpendicular to the plane. So this is going to become my y and my x. Because if I do that, then my a is going to be only in the x direction. So ax will just be a, and ay will be 0. And that will just make everything easier. So to show you how this works. Now it's very important that when you do this, you're only tilting the axes. The forces should still look exactly the same. So, I had force of gravity straight down and the normal force over here somewhere. Those should not move, but I'm going to move the axes. I'm going to make them blue this time so that the y-axis is perpendicular to the plane. That is essentially, it lies along the normal force. And I have to tilt my head a little bit. The x-axis is along the incline surface. Okay. And if you do a little bit of geometry, the 30 degrees ends up being between the force of gravity vector and the y-axis. That's where it always ends up. Okay. So this becomes my my free body diagram. I do need to pick directions. Since I know that acceleration is going to be down the ramp, I'm actually going to make down the ramp like positive x and up. Oops, sorry. Make that positive y and negative x. Remember, directions, you got to pick them, but it doesn't matter what you pick as long as you're consistent with the consequences of your choice. So now when I do Newton's second law in both directions, in the x direction, that's actually going to be a, because I know that the a is like just, it's this way. It's right along x. But in the y direction, I know that ay is 0. Okay. Now, I do have to do a little bit of breaking up. For instance, I've got that 98 newtons there. I'm going to make this bigger. Yeah, I'm going to make this bigger. Let's see. I'll scroll down a little bit. Make that little triangle bigger. So I've got this triangle. Ooh, boy. That was not a straight line. Okay, that's better. I have this vector that looks like this. Okay. And I want to find its components because I need its x component for the fnet x part, and I need its y component for the fnet y part. Okay. Well, I don't actually have to do y to answer this question, but I'm going to do it anyways. So the thing is, I have to make my components follow the new axes. So when I draw these components, they're going to look more like this. Let's see if I can make it match by hand. That's going to be like the y component of the force of gravity. And there's the x component. Note, you can't see me, but I'm tipping my head over. Like, don't be afraid to just tip your head over to the side so that you can see, like, this is a right angle right here. I'll put this on the other side so I can see that's the hypotenuse. Okay. And here's my 30 degrees. So the y component, it's actually adjacent to the 30 degrees. So it's going to be 98 cosine 30. Okay. And the x component is across the triangle from the 30 degrees. So that's going to be 98 sine 30. Okay. So when I go up to fill in these fnet x, well, I'll write these on here too. I've got that one and this one. Okay, there we go. I've got the x component of the force of gravity going down the slope, so I need to write that. And that's it. There's nothing else in the x direction, so I'm just gonna, that's it. That's my equation. Note, it's solvable right now. I can solve for a right now, I am. Okay, it's the middle of the night. What is sine of 30 is a half, yeah. So the magnitude of A is, there we go, is, if I do all that, it's 4.9 meters per second squared. Now, I didn't need the y direction to solve for A, but I might, in the future, need to actually find the normal force. So if I want the normal force, I'm going to have to do the y direction. We'll need the normal force when we start doing friction at the next class session. So we need to know how to find this. So in the y direction, I've got the normal force pointing up. So I write that one down. Minus, I've got the y component of gravity pointing in the negative y direction. So minus 98 cosine theta. I'm sorry, 30. I know what theta is. And then we said acceleration is 0 in that direction. Because that's perpendicular to the surface, and it would be weird if the box accelerated like away from the surface and just like start floating. That'd be weird. And it would be weird if it started accelerating like into the surface, because it would just like dig through the surface. That doesn't make any sense either. So that equals 0. And that makes solving for normal force like super easy. Just move it to the other side. And then pop it in a calculator, which I don't know what that is. 0.8 something times 98. You can hear me getting my calculator out. Times cosine 30. Okay, so like 85 if I round it to 2 sig figs. Oops. Okay. Yeah, so that's what you do when there is an inclined plane involved. Now, of course, this is the simplest inclined plane. It was like just a box sitting on an inclined plane. This can get more complicated, but whenever your object is on an inclined plane, you're going to tilt the axes like this. Now, something that's very common is, we're not going to do this problem because I just want to end this video. It's long enough. If you have 2 objects, that's very sloppy, but if you have 2 objects and only one of them is on an inclined plane, so like here's a modified Atwood machine where the thing on the surface is on an inclined plane surface, the one on the inclined plane gets its axes tilted, but not the one that's hanging. Like this is something to consider individually for each free body diagram. It doesn't have to be all free body diagrams in a problem. Okay. So, on these notes in your class notebook, I do have some problems here out of your book that you could try. I know that's a lot, but like they're there for you to practice with if you want to. But remember, those aren't required and I don't grade them.